Good morning and welcome to Iceberg Summit. Isn't it incredible to have so many of our fellow Apache Iceberg enthusiasts tuned in for today?
It is, and it shows how much Iceberg has become the standard for open table formats, and how much all of you are here to learn and stay up to date with all things Iceberg.
And this is absolutely the place for you to immerse yourself in Iceberg, because I don't know if you've noticed, but we have a pretty solid agenda planned for you today, with a keynote, 2 panels, and 20 top-notch sessions coming your way.
Definitely, we owe this incredible agenda to the more than 200 high-quality abstracts that our speakers have submitted for the call for paper, and to our selection committee, who has worked so hard to review each and every one of them and make this agenda possible.
You know, Kevin, it has been so rewarding to see everyone come together to make this event happen. We really wouldn't be here today without the support and enthusiasm of the entire Apache Iceberg community. So thank you all.
Yes, and a special thank you to our sponsors as well. We really could not have done this event without them either.
And with that, we can finally kick off this morning's keynote. So everyone, I'd like to welcome to the stage one of the original co-creators and PMC chair of Apache Iceberg, Ryan Blue.
Hi, everyone. Great to be here. Today, I want to give a talk about essentially the work that has been going on for the last year in the community to put together Iceberg v3 and give a little taste of what we might be doing after that. But first, I want to just say thank you all for being here at Iceberg Summit 2025. It's pretty incredible to see a room full of 500 people all here in person. I was just saying earlier to Jason that I think 2 years ago I argued, like, we don't need a conference for Iceberg. What would we talk about? You know, it's really incredible to have this moment happening. And so thank you for being here. Thank you for supporting the community. And I also want to thank everyone who, helped make this possible. These things are incredibly complex events. I've gotten a glimpse into how hard they are to put together. So thank you to all the people who have been working tirelessly for months to make this all possible and to have you guys here. So thanks a lot. And also, thank you for everything that you've done and all of the contributions in the last year. It's pretty amazing to see all of this work that's going on. And I think that we're at a really special time in data infrastructure because the fundamental realignment of how we store and operate is continuing. And if anything, it is accelerating in the last year. Now, I know, what realignment, what the heck am I talking about? Let me quickly review. So at Iceberg Summit 2024, I talked about something that I'd noticed, which is that Iceberg's original goal was more disruptive, like way more disruptive than we actually thought it originally was. We set out to make a ubiquitous table format. We said, Hive tables just don't have the behavior that we need. We have zombie data hanging around. We have, unreliable transactions. We can't use these things. And we sort of took for granted this second column, which is shared storage, because everything was unreliable, partly because we were sharing it, and we didn't know that we weren't supposed to do that. So we made this table format that worked in these 3 cases. We made it so that Flink and Spark and Trino and other engines could reliably share storage underneath the hood, which was pretty big because although we didn't realize it at the time, data warehouse storage had never been reliably shared. As a result, most workloads are actually won by data gravity. So this is disruptive in that it's great for you to be able to switch engines and do anything very quickly, but it's also fairly disruptive because people don't really like you being able to easily go from one system to another, although it is really, really important for people actually using the data. So despite some headwinds, what we're seeing is a clear trend towards centralizing data, towards having a central storage bucket in Azure or GCS or S3, and putting all of your data there and allowing access to it through some well-defined protocol. I'm talking about the REST catalog protocol. But so we see all of this centralization, and I think the overall trend is the realignment that I was talking about earlier. We're seeing data centralizing into a single storage area that is governed with a single set of access controls, run by a single catalog, and then specialized compute engines can plug in on top of that framework and that foundation, which is pretty amazing because you can see things like graph databases connecting to the same central data store as Databricks or Snowflake or all these other systems. You've got streaming applications like Flink. So this is a pretty special thing that is happening right now. Okay, get to the point. What I'm most excited about is that I've seen this trend, the trend of Iceberg influencing the vendors in the data ecosystem, right? Everyone is rushing to embrace Iceberg, and that's really great. We're seeing this realignment, the centralization of data, but we're also seeing the after effects of that. So Iceberg is changing the data industry, and now the data industry is in turn turning its focus towards Iceberg and making some substantial investments, and that's really what I want to talk about today. So we're going to go through and talk about V3, the investments that have already been made, and the things that you can expect coming out in the next month or two, and also a little bit of the ideas behind V4 and what we might be able to do in the future. But first, before we get there, I want to pause and say that not everything is V3 related, right? Not everything is pushing the boundaries or adding features to the format. There are a lot of things going on just to make Iceberg tables available in other languages, make them arrow compatible and things like that. So I want to take a minute and review the last year in the Iceberg project. It's been a pretty amazing year. We've had 16 releases, which is more than one a month for an entire year. That's pretty amazing. 250 new contributors. These are people, well, mostly people. I didn't deduplicate the list, and Faco appeared in there like 5 times. But across the various projects, we have 250 first-time PRs in these 16 releases. So that's pretty incredible to have 250 people in a single year. That's, again, like one every other day, getting a PR into Apache Iceberg. We have 7 new committers and 5 new PMC members. And so thank you all for your work. This is a pretty amazing outcome for a year. Actually, not even a year. It's just 11 months since the last Iceberg Summit. So welcome to all our new committers, and congratulations to the new PMC members. Thank you so much for all of the contributions that you've been making. In addition, we've seen some really great work and extensions to Iceberg in basically every area of the project. And so to quickly highlight some of those things, we had a new Kafka Connect module added to the Java project. So now you can very easily sync your Kafka streams into Iceberg tables, and you can do things that you've never been able to before, like multiplex a single stream into multiple tables, automatically create tables as you go, and things like that. So we're really seeing a lot of new capabilities that are pretty amazing. We've added support for Flink 1.2, and we've added Data Fusion Comet, which has a session coming up later today, if you don't know what that is, for accelerating Spark workloads. We've also taken some steps to just maintain the health of the project. So I'm really excited about removing code. So we've removed the connectors for Hive. Hive 4 actually integrates Iceberg natively. And we've removed the connector for Pig, which just wasn't being used anymore. In addition, we've seen very similar amounts of investment in Iceberg and Iceberg Rust. So Iceberg this year has worked a lot on better write features. So now you can write to partition tables. It will now do metadata compaction. They're also working on support for v3 deletion vectors, which I'll talk about in a minute, integration with Rust, and all sorts of things. Rust, similarly, lots of new contributors. I think there's a ton of work going on in the Rust community right now. It can scan, it has integration with Data Fusion. All of these things integrate with the REST catalog, and it's getting better by the day. Two of the newer projects are now up and coming. So we just started a repository for C++, and I'm really excited to talk about Go, which has seen its first 2 releases in the last few months. So Go is now available to interact directly with Iceberg tables. And that also has a pretty high bar for the feature set that it released with. It can already scan and read data, and it can also commit and create tables. Also, there's a talk about Go later on today. And all of this, of course, is a really amazing thing to see because we're seeing these languages come up with REST catalog first. So the REST catalog protocol, which is a fundamental piece of what ties together that centralized story. You need to have a catalog that manages your tables, tells you what they're called, manages things like transactions on them. And now we have a standard protocol for interacting with those catalogs. And as a result, in the last year, we've seen multiple new catalogs and services. There's Gravitino, there's Polaris, there are custom catalogs at different vendors. It is really amazing to see all of these catalogs popping up that are compatible with one another and compatible with all of the language implementations out there. So there's a session on that at 1:30. Please check out some of this awesome work that's happening in the Iceberg community. But let's pivot and go back to what's coming in V3. So this is a narrow set of things. There are more things coming in V3. There are multi-argument transforms and all sorts of exciting things like that. But I've picked out a few highlights that I want to talk about today. So first of all, while we tried when we initially created Iceberg tables to have basically all of the standard SQL data types, we left out some pretty big ones. And so we're just adding them back now. So there are things like nanosecond precision timestamps that are going in. One of my favorites is actually geospatial data types. So geometry and geography columns. I always want to say geology columns, which I guess you could do as well. So these are columns and types specifically for map data. So if you've ever interacted with Google Maps and you've seen the outline of your city or your county or something on a map, that's the kind of data that we need to store. And what we're doing with these types is we're bringing this realignment, centralization of all of your analytic data to the map and GIS use cases. So that's a pretty big deal, and I'm very excited to have worked on it. This was a very hard task, actually, because there's a lot of geospatial knowledge that goes into this. And there's a lot of data storage knowledge. And the intersection of those two communities is, I'm pretty sure, just Dewey Dunnington. So it's really amazing that we actually got this done because I think a lot of us really had to collaborate, work together, and learn about the other side of this. So it is really fantastic. There's a lot of complexity that we actually need to hide in order to make something that everyone can use and can be integrated into even a simple Python program. So what we ended up with is a standard that allows you to specify how you created all of the data, how you ran calculations, but doesn't require the consumer to actually run those calculations themselves. Which is great. So you can integrate with a very simple Python program, push down filters that look like bounding boxes, select all the objects within some area, and that's very simple. In order to produce data, you do need to have GIS libraries installed and hopefully some knowledge of what you're doing, but it's really great that you can consume it very, very easily. Big thanks to Xeon and Gia, who really pushed this through, as well as everyone else here. I'm not going to read out the names. I did that during practice, and it was super boring. But thank you to everyone who worked on this, this feature. The next one I want to talk about is, again, a new data type. And we're introducing these, by the way, in V3 because they're forward-breaking changes, because you can't read the data with older clients. So this has to be in V3. So that's why we're introducing a lot of new data types in V3. Variant is probably my favorite new data type. It is an admission that we've sort of been ignoring semi-structured data for a long time. We have always said, no, you know, the best practice is to schematize all the data in your tables. You should go do that. But we had a lot of challenges in doing that. We had to run things like dead letter queues when you get messages that don't match your expectations coming out of Kafka. And how many people, you know, look at alarms coming off of their dead letter queues? Not very many. So what is special about Variant is that it has the expressibility of JSON. It's a optimized binary format with typed values, so you can send things through without losing precision, without needing to coerce to and from a string. And you can also store the variety of semi-structured data that you have from upstream systems in your tables and work with them at near native or near columnar speeds. So this is great for things like event streams that are coming from maybe deployed devices that you cannot change, because you can't go back to the developers from 5 years ago and say, oh, hey, we need you to conform to our schema. That's just too hard. So what we can do instead is take care of that on the table side, trading some performance, but being able to actually store this data and use it effectively. This is heavily supported by this idea of shredding. So it's looking at the data as it comes in and seeing which columns we should actually pull out to make them proper parquet columns and use in a columnar data store. So this is a really, really powerful thing. And it produces very close to native schematized data performance, but with this flexible schema that can have you know, incorrect types, missing fields, or whatever else. So this is a really powerful new construct within our tables. And you know, please check out Iowa's session later today on it. And also, thank you to everyone who worked on this. This was a big effort across multiple communities, so thanks a lot. I also want to mention we are finally pushing out full table encryption, which is the ability to encrypt all data and metadata in a table with client-managed keys. So we generate keys for every single data or metadata file. We encrypt those keys at the next layer up in the Iceberg tree, and we're able to basically encrypt everything in a table, all the way up to a single table-level key that is managed by KMS. This is, you know, something that many people probably don't care about at all, and we didn't care about for a number of years, but it's very important as the project moves on and matures. A lot of people do have use cases that require encryption for confidentiality. I should mention, we don't support it for authorization. It's just a single key, so it's not like you can encrypt different columns separately. That would be a lot more work, and I'm not a big fan of that pattern, as you can see. All right, two more. The first one is better position deletes. So moving on from types, we have new table features. I'm going to talk about row lineage features as well as position deletes. So position deletes are the ability to, rather than rewriting an entire data file, pinpoint a couple rows in that file and say, hey, those rows are deleted, and rewrite new copies or just simply delete them in other files. So we added these in V2. This was the biggest feature of Iceberg V2, but we left some problems there and we made some mistakes. So V3 cleans up a lot of those mistakes. So first of all, we thought that it would be a really great idea if we changed the model from writing everything out cleanly the first time to being able to offload that work. Do the fastest write that you can and then offload the work to maintenance services. The problem is no one runs those maintenance services, and so we ended up with situations in which tables had thousands of deletes per data file, and that was really not a good situation for performance. We also had problems with the granularity of delete files. So you had two choices. You could either write a delete file for a full partition of data that was partition scoped, or you could write a delete file that was file scoped. So in those cases, though, we didn't really have a great situation. So if you wrote per file, you created a delete file per data file per write, and that was a problem. And if you wrote for each partition, you had so many false positives that you had this explosion again with the number of delete files you had to apply to every single data file. So the big lesson learned was we need synchronous maintenance. We need to maintain these delete files and require engines to have a single delete file per data file every time. We also were able to use the new Puffin format to store the new format. So we said, let's get rid of Parquet and not do this unnecessary translation because we're already using roaring bitmaps in memory. So we got rid of the unnecessary translation, and we allowed coalescing a file-scoped delete vector across multiple partitions in a single Puffin file. And we were able to do that by tracking each individual deletion vector, even though we had gathered those into larger files. So there's a talk by Anton later today to explain all the gory details of this, but the big takeaway is that deletes in v3 are simply going to be a lot faster because you're not accumulating deletes, you're forced to pay the price of maintaining those deletes over time, and that's just a whole lot better for read performance. Thank you to everyone who worked on this. This was a huge cross-company and cross-team project with a ton of reviews and oversight. We had people from all of the biggest open source engines involved in this, and I'm really happy to see it get done. All right, next, row lineage. So even with DVs, we found that reconstructing changes is hard. So if you want to stream the changes that happen to your Iceberg table into a Flink job or mirror those changes elsewhere, we found out that that is still really hard. Now, DVs actually make this a whole lot easier. I didn't make this point on the last slide, but if you have a single DV against a data file, then it's much easier to reconstruct the rows that were deleted in a given commit because you're diffing 2 delete files rather than diffing thousands of delete files. So it's really nice to be able to have DVs. But even then, we have problems. If you're using copy on write, then you have a whole bunch of rows that are both in the old file and the new file. Which ones were modified? Well, if you do what we do today, then you have to compare each value in every single row. And that's not fun. That's actually really slow. Same thing, we don't have any way of matching up the rows that changed. So you would actually have to compare every deleted row to every added row and try and figure out what was changed or what was added. Not only that, you could take information from the on clause in your SQL, but that's just complicated. So it's a hard problem to reconstruct the changes today. So what we want to do, though, is make it possible to incrementally consume tables and also see the changes so that you can look at some output of a merge statement and know exactly what that merge did to every row. That's really important for debugging. So what we've added in v3 is an implicit row ID. So every single row as it gets added to the table is implicitly assigned a row ID. And we also track the last updated sequence number for every row. So this addresses the 2 problems I pointed out on the last slide. The last updated sequence number allows you to tell which rows were actually modified in a given commit. And the row ID allows you to match up the deleted version of a row with the added version of a row and see that change or that update. So this is a really powerful tool, and it's going to be really great to start building on this in V3. So again, thank you to everyone who worked on this feature. It's really good to see it going out. This is a complex one because you have to inherit metadata down the tree, and it's not a simple thing. But what we ended up with, I think, is going to be a really powerful feature for the Iceberg community. Now, my favorite thing about V3 is actually not the features that we just went over, although variance is really going to save a lot of people some time. The best part, though, is the investment that this represents. So I'm going to go through these things again and sort of point out what I'm talking about. So variant was created in the Spark community by Databricks, proposed and picked up by Snowflake. We decided collectively that we should move the spec into the Parquet community because it's upstream of so many projects and where you really want to standardize a lot of these things. It was reviewed by people from Databricks, Google, Snowflake, SingData. This was not a simple thing to get through. And in fact, we're still tweaking and finalizing the standard. But the end outcome is that this is embraced by both Iceberg and Delta. So we have, we're starting to move forward with these formats aligned. So we're using the exact same on-disk representation in Iceberg and Delta for a very complex feature. Same thing in Geospatial. We worked with the Parquet community across very, very different companies. Apple, Whereabouts, Databricks, Voltron, Snowflake. There are so many people working on these things. And we did these both in a way that worked for both the Delta and the Iceberg communities from the get-go, which I think is really, really important for people with data in both formats or that want to move between one or the other. Same thing with deletion vectors. So deletion vectors, the format that we use, was actually pioneered by Delta, and the Iceberg community chose to be compatible with that format. The Delta folks from Databricks were really handy, and they were consulting on the Iceberg spec the whole way and giving advice about what worked in Delta and what didn't so that we didn't make the same mistakes. We had a huge community of people that were validating these things. And the same thing with row lineage. It was proposed by Snowflake. It was reviewed by some of the Delta folks from Databricks to make it compatible with the existing feature that already was in Delta. So it's pretty amazing to see the Iceberg and Delta communities not coming together. It's not like we're sharing code. It's not like we're, or merging the PMCs or anything like that. But it's great to see that the Iceberg and the Delta communities are coordinating, right? We're building these features so that they will be compatible from the get-go. And in fact, what V3 actually delivers is this common data layer. This is the Iceberg half of the common data layer, where you can take Delta files and put them in Iceberg, and you can take Iceberg files and hopefully put them in Delta and not need to worry about rewriting anything at that lowest level, the petabytes of data that you have sitting in S3. So I think that that is a huge step forward, and I'm really excited about this idea of the two communities actually coordinating and not competing. And we'll see how that's even more powerful later on as well. So now let's take a minute to pivot again and talk about what could possibly be in Iceberg v4. Now, let me start by saying this is where we kind of go off the rails a bit, because I don't know what's going to be in Iceberg v4. I don't think anyone does. So these are definitely my opinions. These are things that I hope that we work on. These are sort of the problems that I see in the community. So hopefully this is what we're working on in v4, but take this with a grain of salt. I'm just one person, and these are my opinions. All right. So the problem. It's hard to admit, especially for me, because I made a lot of these mistakes. But Iceberg metadata is showing its age. Definitely is. There are certain things that we did to simplify the format at first, because you can't do everything all at once. But now we are sort of seeing, as we get more and more people using the format for a broader set of use cases, it's not just huge data, not just petabyte scale tables. We're seeing people that want to use Iceberg for smaller data sets. And to be honest, it's not great. It could be better for small tables. And there are a lot of small tables out there. Dimension tables in basically all of our environments are small tables, essentially. But the problem is, for any one of those small tables, you have to read, generally, at least 3 different stages of files in order to plan a scan. You have to go to the catalog, and that might read a file. You have to read the manifest list. Then you have to read a manifest to get all of the data files, and then you have to go read those data files and do the actual work of a query. So that's not great. And you have to do it in that order serially. You can't parallelize those things. Then on the write side, we have the same problem. Writes each create a manifest list and at least one manifest. But sometimes they also rewrite a whole bunch of manifests in order to delete files. Well, we just took care of rewriting whole data files by introducing DVs. There's probably something better we can do there. And writes also produce small manifests. So in order to do the least amount of work possible, again, sort of mirroring the DV case where we did the least amount of work possible by allowing you to write multiple DVs into the table, we write just a new manifest every single time you append data to a table. And that ends up producing a lot of small manifests that are then compacted as part of a later commit operation. Delays one commit and produces a whole bunch of small files. Again, not great for small tables. So I think that we can do better. There are also other ways in which we can see that Iceberg's age is showing. So first of all, we care a lot more about disaster recovery these days. And Iceberg, you can't simply pick up data files in one bucket, move them to another, and have them work. You actually have to go rewrite the metadata, and that is rewrite every metadata file to write the new file paths. There are some hacks, but I would not necessarily recommend that. So file replication doesn't work. Metadata has to be rewritten. Then we also have representation issues. Column bounds are just binary blobs. This has bitten us in the last year because we actually can't add certain types of schema evolution without incorrectly interpreting those binary blobs. So we weren't able to add cases where you can go from, say, integer to string because we didn't know how to interpret the binary underneath that integer. So that's a problem. We also don't have the ability to have alternative sort orders for things like matching on the lowercase of a column rather than always being case sensitive. I also think 2 other things. Scan planning could always be faster. And the slowest part of scan planning is that we're slogging through reading and reconstructing a whole bunch of lower and upper bounds values that never get used. So maybe we can skip those. And then finally, metadata skipping was built for a partition-based world. And we're kind of moving beyond that with clustering and z-ordering and things like that. Not to mention the fact that it just doesn't work at all with Geospatial, which doesn't cleanly partition. So because you have objects that might be vastly different sizes, you can't just chop up the Earth into a grid and then store an object within some grid space. So how do we move past some of these issues? Well, here's what I think we can do to do better. So first of all, let's review the original metadata structure. This is V1, but it actually, a lot of people are still using this. So you have the Iceberg table, and the metastore is simply a pointer from the table name to the metadata root file. And then you have one or more snapshots, each of which is represented by a manifest list. And then you have manifests that get reused across versions and point to the eventual data files. As I was pointing out earlier, you've got to read a lot of files in this case. And you've got to read them in order, V1, S1, M1, then the data files. Now this gets better because the root metadata JSON was getting large and unwieldy, and if you wanted to do things like change the schema and write to the table at the same time, we were seeing conflicts. So we moved metadata to be managed by the REST catalog. And this is a whole lot better because you can commit to this 2 branches in a table without conflicts. So this allows us to do server-side commit deconfliction. Simplifies the metadata structure somewhat, although we still want to keep those JSON files around just so that you have something that makes the table, ultimately portable, should you want to move catalogs or something like that. But this still has all of those issues that I was mentioning earlier. So the idea behind v4, at least in my head, is what if we allowed a single metadata layer? And we said, okay, we're going to track data and metadata files in any manifest. So we have this ability to move A and B here into the root of the tree. Well, that's going to work a whole lot better for small tables because we'll simply copy a whole bunch of the metadata over and over again. But the copy is the cheap part because storage is cheap, and really we're not going to accumulate so much in this root level manifest that it exceeds that your cost exceeds the latency to and from S3. So this is going to be better for most cases. And then what if we also allowed that to be adaptive? So that when you had this root manifest get too large, you simply split out another manifest and managed it that way. Now this has a lot of benefits. First of all, you don't actually need to go and compact metadata anymore. You're constantly accumulating new files in the root, and then you can see at a later time when you're maintaining this, which files should move where and which manifests you might need to rewrite. So I think that this structure is potentially a game changer and addresses a lot of those issues. I mean, there are quite a few issues with the v1 metadata. So unified manifests allow us to have lower and upper bounds with even the metadata files. So we'll have those column bounds, and that'll be geospatial friendly. It'll also allow us to do things like data and delete files in the root, not need to require manifest compaction, which is not something that is widely supported across the implementations anyway. I just mentioned that in the last year, Python added manifest compaction. And this structure with longer-lived manifests allows us to use DVs to delete data files within those manifests for faster, or essentially not needing to rewrite all those files all the time. The adaptive metadata tree also gives us one file commits, much more friendly for small tables, and doesn't need metadata compaction. And then the other 2 things that I would change are, number 1, moving to columnar metadata. So being able to skip the unused statistics, have typed lower and upper bounds for alternative sort orders or better treatment of variant and some of these well-structured data types, things like that. And then finally, we've been talking about it for long enough. We should probably support relative paths in metadata so that you can pick up the files for a table, move it somewhere else, and have that table simply work. So those are the things I'm interested in v4. And hopefully, you guys think those are good ideas as well. Now, I just want to mention one last thing, that I'm really only thinking about this because we're cooperating with the Delta community. Working with Delta and the folks at Databricks has really pushed us in the Iceberg community to accept that some of these constraints are not trade-offs, they're actually problems that we can solve. So I think, well, my attitude used to be, oh, those Delta guys, yeah, no one needs writes that are that fast. You're gonna create tiny data files. You're gonna, and those concerns are valid, right? You don't wanna commit too quickly to a table and things like that. But what we were blinded to, what I was blinded to, was that these are problems, right? Maybe no one needs to commit that quickly, but a single file commit is really important for small tables. So we weren't seeing the other use cases that would have gotten better from looking at these problems as problems to solve. We were looking at these problems and saying, Iceberg is read optimized, Delta is write optimized, and we were thinking adversarially. So I think that the cooperation across communities has made us see these things as challenges that we can solve. And we actually can. I'm excited about v4 metadata because we're going to make the formats generally better. And my goal here is what it always has been, to make Iceberg a ubiquitous table format that is suitable for all of these use cases. And I'm really happy that we're being pushed, and we're seeing these as problems and challenges that can be solved. So I'm really excited about that. I would love to get to the point where we can put Iceberg metadata into the Delta format in certain structures. Use Iceberg for things like Delta checkpoints. I'm very excited about the things that we can do now that we're working together. So I'll leave you with that. Thank you for listening.
Thank you, Ryan. What an incredible session. It's truly inspiring to see the latest developments and the amazing group of people driving innovation forward. Thank you so much.
Great to be here.